So I'm going to walk you through some things we've been working on recently, me and a few others, on trying to respond to changes in architecture for a standard and difficult problem in computational physics, which is solving Poisson's equation. So here's a picture of a sort that you've probably already seen multiple times, which is the summary that power constraints are leading to new HPC architectures. If the kind of conceptual cartoon of what an HPC architecture looked like 20 years ago is on the left. You had a little homogeneous processor, you had some memory attached to it, and these things were hooked together on a network. What's happened is that this has now exploded into something much more complicated. You've got thin cores and accelerators, just a little red circle here. You've got multiple thin cores, you've got accelerators, you've got different kinds of memory, DRAM, non-volatile RAM, 3D stacked memory, lower capacity, higher bandwidth, and then the usual communication going off chip. So why is all this happening? The reason is that we can no longer make the clock speeds faster on computers, on processors. They kind of topping out at about 4 gigahertz. However, we can still continue to pack more and more transistors onto chips, and so we can add more transistors, add more things that do stuff onto a chip. So that's because Moore's law is still in operation. Well, that's supposedly going away soon, but it's still there. So what are the consequences of this from the point of view of programming? Relative size of the memory decreases. You don't have as much memory given the amount of floating point capability. The memory architecture becomes more complex in ways that can't be completely hidden from or ignored by the application developer. Thank God it can be hidden to some extent because these are very complicated systems, but you can't completely ignore it. And the kind of general rule is that flops are over-provisioned relative to data motion and data storage. So this is an idea now at about 10 years old for how to summarize and provide a cartoon for performance for these kinds of architectures. In fact, for a large number of processor architectures, and this is due to Sam Williams et al. From about 2009. This, by the way, I'll start with an advertisement for cartoons. All performance engineering is done via cartoons. You cannot possibly imagine how complicated a processor is, but you can comprehend a cartoon, and if you're lucky, it's a faithful cartoon that provides a useful guide for performance. This is an example of something that we're trying to find out, can it really provide a useful guide for performance? And so far the answer appears to be yes, with some caveats, and you'll see some of the caveats as we go along. So what is this cartoon showing you? It has a name. It's called the Roofline model, and it's just a bunch of straight lines on a graph. The axes of the graph are gigaflops per second on the vertical axis, and flops per byte on the horizontal axis. So this is going to be in units of a particular processor. So this turns out to be for the Haswell processor, which is the processor on Cori phase 1 at NERSC. So what are these lines telling us? What these lines are defining are upper bounds on your performance, and they all come in several flavors. So the idea is that if you are reading and writing data out of DRAM to some higher level of memory and ultimately to the processor where the work's actually being done, if you don't have enough floating point to, if you don't have enough floating point work to amortize the cost of reading and writing out of memory, you will be limited by the bandwidth in and out of DRAM. So here's the way of reading this graph. If this is the number of flops per byte of your algorithm, and most, say, classical algorithms for grid-based methods are around 1, then then what's going to happen is that the way you read this is whatever your number of flops per byte is, you get to that point, you move up on the graph, and the line that you intersect is the place where that's going to bound your performance. So if you're at 1 flop per byte, even though the actual maximal performance for this particular processor is around 845 gigaflops, you'll only get about 100 gigaflops. And that's because you can't feed it enough data to keep all the processors busy. Now, on the other hand, if you're over here at 10 flops per byte read or written, then you're good. You can actually achieve, it is possible for you to achieve the actual maximum speed of the processors. By the way, this graph here is not a theoretical construct. This is actually something from generated by something called the Empirical Roofline Toolkit. And what it does is it runs a particular very simple streaming benchmark combination of reading and writing out of memory and doing simple arithmetic operations to get measured versions of these things, of these lines, of these bounds. So the 845 gigaflops per second is not the kind of the advertised speed of light for the Haswell processor. It's about, I think that's about 1.4 teraflops. But this is actually what you measure with the tool. So what can you do about that? So first of all, this tells you gives you an idea of, given an algorithm, if I can define what I mean by flops per byte for that algorithm, what's the best you can possibly do? And that's useful for lots of different reasons. One, it tells you something to aspire to, but also it also tells you when to give up. That is, when am I going to stop trying to do performance improvements? Well, if I'm at 1 flop per byte, I'm not going to get above 100 gigaflops. Just get over it. On the other hand, this is only a threshold. This is only a bound. And the bound is is something that you probably can't exceed, but it doesn't mean that you'll get there easily. And we'll see an example of this going forward, multiple examples of this going forward, in fact. And there's also kind of a flops per byte threshold around 8 for this processor that says below that you can't do any better, you're going to be memory bound if you're coming out of DRAM. By the way, there are other lines too for faster levels of in the memory hierarchy. There's a roofline bound for running in and out of L3. It's almost a factor of 10 better than, in some sense, than what you get out of DRAM. So these are all there, and then L2 and L1. Now, where processor architecture is going, simply put, these red lines aren't moving that much. They're going to be the bounds we're going to be living with for the next several years. On the other hand, this blue line is going up because you just can put more floating point capability on a chip, and that means you can do more flops. So what's going to happen is that there's going to be considerable incentive to try to move your algorithms over in this direction, over to the right, in order to take advantage of having proportionately more floating point relative to having to your your ability to move data around. So the next is going to be, the rest of this talk is going to be an example of trying to do that for a classical problem. So now, I will, if it'll become very obvious to you, and we'll start now that I'm a mathematician who likes to program, as opposed to a chemist who likes to program. So this is Poisson's equation. This is something that we all that many of us have to solve in lots of different settings. You can view it as solving a partial differential equation, Laplacian phi equal f, solve for phi, or you can view it as computing the convolution with a Green's function. phi is equal to g convolved with f, which is the integral of g of x minus y f of y dy, where g of z is the classical Coulomb or Newtonian potential. Now, if you were to take this form of the equation, a naive implementation of that just using quadratures on n points would lead to an order n squared calculation. However, there's something really special about this kernel. And in mathematicians' terminology, it's local regularity. That is, the field induced by a localized charge is smooth away from the support of the charge. In fact, the derivatives fall off at some polynomial rate, and the polynomial rate gets better and better for the higher derivatives. It's actually better than that. For Poisson, this is actually a real analytic function. You have local convergent Taylor series. So here's a typical kind of thing you will see, support of f with diameter d, and you're looking at distance L, and the kth derivative of phi is going to be d over L to the k1 plus k2 plus k3 plus 1. So it's decaying at that rate. Exploiting local regularity leads to fast order n log n methods. All n log n methods almost obviously exploit this fact, the fact that if you look at charges, if you look at two disjoint regions, the way they interact is almost decoupled. It's decoupled modulo smooth functions. And so you can use that fact to make a reduced representation of that coupling and thus go from n squared to n log n. Multigrid is based on that. Fast multipole is based on that. Tree is based on that. You even can dig at that a little bit, and there's a sense in which FFT is based on that, although it's a little hard to see directly. So what I'm going to talk about are structured grid discretizations for Poisson. And all the ones I'm going to talk about are based on finite difference discretizations of Laplacian, a special class of them called Mehrstellen discretizations. So here's just a standard kind of finite difference discretization. Laplacian h phi h is equal to the sum of shifts. So you shift by some tuple s, or you multiply by a coefficient that depends on the amount you're shifting. Multiply that times phi of g plus the shift, and then sum over some set of shifts. So 7-point operators in 3D, other things look like this. There's a special class of these things, as I said, called Mehrstellen, where the truncation error has a very special feature. So if you say, find out what the difference is between Laplacian of phi and Laplacian h of phi, where phi is now some function evaluated on a grid. That's truncation error. It's related to solution error. It's a measure of how accurate your operator is. Well, in this case, what you get is a very special series expansion for the truncation error. It all looks like operators applied to Laplacian of phi, not operators applied to phi, up until you get to some very high order, capital Q, which we call the harmonic order of accuracy. And what's the point of this? Well, if what you're interested in is high order accuracy on harmonic functions, then you can get these very high order accurate methods on harmonic functions relatively cheaply. So for S, is the floor of Q over 4. That's how, in order to get to that order, that's how big S has to be. So for example, if you just have a 3 by 3 by 3 stencil, I can cook up a stencil that is 6th order accurate on harmonic functions. That's actually classical. It's in Kolotz's book on numerical methods. Then you can go farther than that. If you can go to 5 by 5 by 5, I can cook up one that's 10th order accurate. And that sounds crazy, but remember, what we're going to be using these for is to represent the coupling between disjoint regions, and that's very smooth. So it's actually relevant that we can get up to 10th order. Now, something else that's perhaps not obvious but true is that just as you can define discrete Laplacians, you can define discrete Green's functions. GH convolved with FH is just you can convolve with a kernel, a discrete kernel, And that's the same as applying Laplacian H inverse to FH, where everything's on a grid. So you can figure out and effectively compute discrete Green's functions that you can then convolve. Okay, so let's start out by saying why are we doing this? And the root of why we're doing this is kind of exposed in multigrid. So what's multigrid? Multigrid, from the point of view of this discussion, I'm going to say it's multigrid in parallel. What we do is we're trying to solve Poisson's equation on some domain. And the first thing we do is we break the domain up into patches. Each one of these little boxes is a patch of grid, so in 32 squared, or in 3D 32 cubed, let's say. And I'll be doing domain decomposition about that with that to do things in parallel. Don't worry too much about that, because the parallel aspects of this, or at least the distributed memory parallel aspects of this, are not where the problem is. So what is multigrid? It's iterate to convergence the following procedure. That you do point relaxation, you take lambda times the residual of your current guess, and increment phi with it, and you do that p times. The second thing you do, this is what makes multigrid, is you solve a coarsened problem. And I've written it in a slightly more general way than is customary for Poisson. In so-called full approximation scheme form, I compute a right-hand side, which is a coarse grid Laplacian, 2h coarser, factor 2 coarser. Take the average of phi onto the next coarser grid, apply that Laplacian, and then average the residual, take the sum. And now I solve that. So that's do a solve on a factor 2 coarser grid. I interpolate a correction. I take phi c, whatever I came out of that solve, and I subtract off the average of my phi that I started with and interpolate that correction, and then I do point relaxation again. So the way to think of this is that, first of all, each one of these steps is a loop over patches. So the problem from the point of view of our kind of limiting communication is that every one of these steps you're reading in a patch, you're doing something not very big to it and writing it back out again because you have to save it. That generates a huge amount of communication or data movement relative to what you would think would be ideal. So let's put a number to that. Data moved per grid point in bytes is the number of iterations, how many iterations it takes to converge. If you're doing a standard multigrid V cycle, you get about an order of magnitude improvement in the residual for every iteration. So let's say 10 iterations to get 10 digits. So it's the number of iterations, 10, number of bytes, 8, and then point relaxation reads in 2, writes out 1. Relaxation reads in 1 and writes out 1/8. Interpolation reads in 1 1/8 and writes out 1. This may be 2 then. So in any case, though, this is about on the order of several hundred, 640 by this estimate, and I may have that one may be a 2. So it would be 720. And every step requires moving data to and from main memory. And the reason is that you're assuming that you're doing a problem that you can't just have a single patch in L3. You actually have to you do something, there's not enough room in your higher levels of your memory hierarchy to store everything, so you have to write it out, or the system will write it out for you if it's a cache system, to make space for the next, for the next set of data to be processed. Now, how many flops do we have? Again, it's number of iterations, size of stencil, 7 to 27 points, and times the number of times you do point relaxation, and then the stuff you do for interpolation and coarsening, and when the dust settles, again, with the assumptions we made, 300 to 1,200 flops. Do the math, the arithmetic intensity is 1/2 to 2. So let's go back up here. Oh no, that's not the direction I wanted to go. That would have been approved. So 1/2 to 2 is going to be down here. As I said, classical things are on the order of 1 flop per byte. So it's going to be 100 gigaflops, 80 gigaflops. If you get up to 2, it'll be 200 gigaflops per second for a whole node. That's a factor of 4 under what you would get from the peak, and maybe it's reasonable to give up a factor of 2 because you're not going to get all your fuse multiply adds, but anything below that you should be a little concerned about. So is there any way to change the way we do this in order to better exploit local regularity to reduce data motion? This argument here says that the coupling is so smooth, it should be representable by a small number of degrees of freedom. But it's not. It's not being represented that way in multigrid. That's the assertion is that's an artifact of the specifics of multigrid, not what you have to do in order to solve the problem. So here's a second algorithm. Looks very much like multigrid structurally, but it's different. And it's different in a way that is favorable to what we want to do. We do a lot more floating point operation and a lot less data motion. Comes with a price. So, and I'll discuss that. So again, it's domain decomposition into patches. First step is to compute the solution, a local solution on larger overlapping patches. So here's a patch for one of the patches, and I'm going to compute G convolved with F on this red dotted box here. So, and this is actually the approximate size. It's about a radius of 2 in max norm. Now I compute a coarsened solution, very much the same way I did in multigrid. Phi c is equal to, I've coarsened by a factor of 4, not 2. And then how do I get the right-hand side? Well, I take the coarse operator and apply it to a coarsened version of the patch data. And now coming back up, I'm going to now solve, I've computed this solution. Now I compute boundary conditions on each patch and solve again. It's cheaper for me to do solves than to move data. So rather than doing it as I did in multigrid, which is interpolate corrections, I just interpolate a fixed up version of the solution on the boundary of a patch. I have to move less data, I have to store less data. And then I solve just a Dirichlet problem, Poisson, on this little patch again. And I'm done. There is no iteration here. So I have to justify that this actually makes sense in terms of the error you get. I could do lots of things that have less communication, but they wouldn't be correct answers to the problem. But let's first do some counting. The data moved per unknown is about 150 bytes. So it's a factor of 4 or less than what the data we're moving for multigrid. So that's good news. And the reason we're getting that is even though we're computing this huge convolution, remember it goes like the radius cubed, we're only storing the results from this initial convolution on a coarsened grid, coarsened by a factor of 4. That drops it by 64. That's nothing. And on boundaries of patches, that drops it by surface to volume, also a big multiplier. Number of flops we're doing is large. It's 5,000. And it's mostly in the initial local convolutions on large patches. What's the AI we get? We get 33. So here's what the Roofline tells us should happen. So here's multigrid. This is multigrid with 7 points stencils. Here's multigrid with 27 point stencils. And again, what Roofline predicts is 200 gigaflops down to maybe 80 gigaflops for a 32 core node. Over here, here's MLC at an arithmetic intensity of 33. And I put a line here because if you look at the operation mix in computing those convolutions, it turns out not to be one add and one multiply. It's a mixture of like 3 to 1 or 4 to 1. And so you can never get the full 845 because you're not going to get all the FMAs. But 445 is a legitimate Roofline for this. I should expect to be able to do this. So let's see. So just a sideline here. There's an old algorithm that I think should be having a comeback if it isn't already, which is Hockney's method for computing discrete convolutions. I'll just say it in 2 words, which is that if you're computing a discrete convolution where one of the things you're convolving has a nice bounded charge, then you can do that cheaply. You can do it in order n log n operations because FFTs diagonalize convolution. The price you pay is you have to pad out how big a region you're doing the convolution in, but no more than you would expect. If you think of convolution as being a fancy stencil operation, you just put in a number of ghost cells for the stencil operation so that your stencil can't see that the boundary conditions are periodic. So that's why we get we can get even 4,000 floating point operations per unknown for such a relatively large convolution. So here's the price. I told you there was a price for doing this. And the price is, here, our error analysis, our error doesn't look like what the error looks like in classical difference methods. In classical difference methods, you converge like some power of h, and that's it. The finer you make the grid, the better the power of h, or the smaller the error. It's the same power of h. Here, there's a second component to the error. Here you have h to the q, and then we have something that is not a function of h, because here's my coarse grid spacing, here's my fine grid spacing. I'm holding that fixed. That's 4. N is the number of grid points in my patch, and alpha is the amount I grow it by, the overlap. So this number here, raised to the qth power, is a localization error, and it's order 1. But in fact, as you will see, it's order 1, but it's small. And furthermore, I have knobs I can use to control it. I can change alpha, I can change my patch size, and the fun one is that I get to change q. But it has different error properties, and you have to know whether you can tolerate them or not. If h is above some threshold, you'll see the solution converge like h to the q, little q. If h is below some threshold, the error saturates. This is what we call localization error or barrier error. And as I said, there are lever arms here. Alpha, n, and q. This shouldn't be r, it should be n. And q are lever arms that trade off performance and accuracy, and in different ways. Using a larger patch size may be less flexible in some respects, but boy, does it reduce this barrier error. Double the patch size, you reduce the barrier error by 1/2 to the q. Just again, another plug for the math. We observe a rapid decay and truncation error of the operator as a function of max norm distance from the charge. So if you take the continuous Laplacian applied to the Green's function, it's 0 everywhere except at the origin where it's a delta function. Now, if you take the discrete Laplacian and apply it to the continuous Green's function and say, how big is it? What you see is that it decays very rapidly. And how rapidly is an inverse power law that depends on the order of the method. So for q equal 4, this is the magenta curve. Q equals 6, it's red, and q equal 10, it's blue. And it's actually what's predicted from the kind of truncation error analysis plus decay of derivatives. There's a piece of magic in this error analysis that led to that, or in this decay rate, this discrete potential theory, that led to that error analysis. But I'm not going to try to take you through that because I've probably done more algebra than I can legitimately do in a dinner talk. Now some results. So first of all, I made an assertion that this barrier error is acceptable. Here's some indications that it is. So the local error. So we can adjust kind of the kind of h error in that little q by deciding, it can be up to capital Q. It's a little inconvenient to make it that large, so we've typically fixed it to be little q equal 4 for all of the runs, so that we have a clean comparison. So here's a uniform grid, relatively smooth test problem, and what we're plotting here is error. Here's 10 to the minus 7th down to 10 to the minus 11th as a function of the inverse mesh spacing at the finest level. And this is h to the minus 4, so you see you're getting 4th order accuracy, and at some point it cuts off. And it cuts off as predicted by the theory. If you're at q equals 6, it cuts off up here at 10 to the minus 8th, between 10 to the minus 8th and 10 to the minus 9. If you're at q equal 10, it cuts off much farther down, 10 to the minus 10, 10 to the minus, below 10 to the minus 10. And there are various other trade-offs. If you stay at q equals 6 and take n equals 64, so double the patch size, again, that has a big moment, a big lever arm for your error. You're down here in that area. Now here's another calculation, and this explains, by the way, why people would do anything like multigrid or anything else. Is because you can do things like adaptive gridding with multigrid that you can't do, for example, with an FFT. So this is an adaptively refined grid. The finest grids, which are you can't really see the outline of, are underneath these three balls. It's about 0.2% of the total region is refined at that level. And again, we're seeing the same sort of error behavior. And the major takeaway from this is, yes, this is behaving as we expected from the analysis. And the second one is that for reasonable values so the q equals 6, alpha equals 3.25, n equals 32 is kind of our baseline for doing our performance analysis. 8 digits of accuracy, we can live with that for a lot of problems. Furthermore, the kind of error that you get is, I said that it was representing the smooth non-local component of the error. Here's some indirect evidence of that. So here you're refining from the place where you're still in the asymptotic regime, q equals 6, n equals 512, and now you've refined to q equals 6, n equals 1024. We're plotting the actual solution error here. And here's what's happening. You still going from here to, if you were doing an ordinary refinement study, you would see this kind of plot. The picture would not change in the slightest. What would change is that the range of values this represented would go down by a factor of, well, for q equals 4, 16. But here, the solution changes. And what's happening is that this part of the error is going down, and the residual smooth barrier error is remaining. So this is indirect evidence, and pretty good indirect evidence, that not only is that barrier error there, which is not great, but it's also smooth. And smooth is helpful if you're going to use this in other problems. You're going to take differences, so if you're computing a potential, and you're going to take differences to compute fields. You want the error to be smooth, otherwise you will start introducing noise as you take differences. So how does this scale get you the performance you asked for? The answer is yes. So here's our baseline performance case. Q is equal to, capital Q is equal to 6, alpha, which is the radius, is 3.25, n equals 32. The plots are wall clock time to solution in seconds versus number of cores on Cori phase 1. And red lines represent perfect scaling. So this is strong scaling, 10 to the 9th grid points and applying 64 to 4K cores. And again, there are 32 cores to a node. And we're seeing greater than 60% strong scaling efficiency over that range. When we're up at 4K cores, we can compute 1 billion mesh points at about a hair less than a second. Here we're doing weak scaling, and these are, by the way, all adaptive calculations. Here we're doing weak scaling. So every time we increase the resources, we make the problem size larger. And this is replication weak scaling. So what we're doing is stamping out copies and putting them adjacent to each other of these charges. And it's for adaptive methods, you get more predictable sorts of scaling results from doing that kind of scaling. And for a lot of applications, that actually is what you're doing. You're computing ever larger domains, not computing on ever finer grids. So this is, starting out here is 10 to the 9th grid points, and we get all the way up to 500 billion grid points, and we're weak scaling up to that point within 8%. And the equivalent resolution of this as an adaptive calculation is about 2.8 times 10 to the 14th unknown. So if we tried to do this on a rectangular grid, a uniform rectangular grid, it'd be hopeless. So this is demonstrating adaptive works and scales. Now here's a performance comparison. Cori phase 1, 32 cores per node, 8 nodes. 10 to the 9th unknowns. It's essentially the courses case, the strong scaling case we just looked at least for MLC. For multigrid, so we compared this with the HPGMG non-adaptive benchmark, 1 billion mesh points, 10 V cycles. Took 9 seconds, And what we saw was, what we measured was about 17 gigaflops per node. So the roofline bound is 200 gigaflops. So that's not good. It is what it is. This is a very carefully designed and developed benchmark, but this is as good as it gets. And the reason why this is the case is still a little bit of a mystery to us. In the MLC case, we see a similar phenomenon, although everything's faster. Again, 10 to the 9th unknowns, both uniform and adaptive cases. 10 to the 9th unknowns is 8 seconds, so we're about at the crossover point with multigrid here. However, because we're doing a lot more flops, to get 8 seconds, we actually have to go a lot faster, 70 gigaflops per node. The Hockney kernel, the thing that does that convolution, runs at about 3.64 seconds, 140 gigaflops per node, and the roofline bound for that is, as I said, 455 gigaflops. So we're also not achieving the roofline. Why not? Well, in the MLC case, the problem is buried in the FFT, because if you want to get SIMD out of FFT, what you need to do is unravel the real and complex parts, which are stored real, imaginary, real, imaginary, real, imaginary, and that is putting a lot of stress on the load buffer, on the load and store buffers, to unravel that and put it back together again in order to get to execute SIMD instructions. Now, there's an obvious cure for this, which is use a split representation of FFT, real array, imaginary array. But that standard FFTs like FFTW don't do that. Well, they have an API that does it, but what they do is they copy it into the other form, and that doesn't help us. What?
I just assumed it did the split. That's obvious.
It's obvious, but not correct. I'm sorry to say. It didn't matter. Think of FFTW as targeting, superscalar systems of 20 years ago. This sort of thing didn't matter. Remember, they weren't even thinking SIMD at the time. And so SIMD was a retrofit to FFTW, and this was the simplest way for them to do it. Now, what else do we have? And that accounts for this 140 versus 455. And in fact, the headroom for the Hockney is huge. The actual AI just for the Hockney kernel is about somewhere around 500. We read in very small amounts of data and write out very small amounts of data at the expense of doing a lot more floating point operations. And then probably the data choreography of copying these things on kind of codimension 1 surfaces needs more squeezing, and we're up to that. There are a bunch of algorithmic details, such as using Mehrstellen stencils. We don't do a full convolution. We do a convolution on a kind of smaller box. And for the larger box, we replace the full convolution by the convolution of the low order, the first, say, up to 4th order terms in the Legendre expansion. That says you have to do much less moving of data between processors, because all you have to do, and much less convolution, because all you have to do is move those Legendre coefficients, and then the FFTs, the convolution with G of the Legendre expansions are pre-computed and stored. Another thing we had to do was, how did we get this to run fast? Well, a key thing to make it run fast is that originally the first thing you do is you say, okay, we'll run it flat MPI. And of course, you don't want to run flat MPI on a multi-core system. So the next thing you do is you say, I'll run multiple threads, but I'll assign 1 patch per thread. Turns out you don't want to do that either. And the reason is that that means you'll have 32 threads, each of which is processing a patch. That means you're sharing the L3 across 32 different threads of control. What we did instead is took the 32 threads, have 8 threads at a time working on a single patch. That allowed the single patch to fit into L3 for the entire Hockney calculation. And that was a huge win. That was our factor of 3 in Hockney. And that's what kind of put us over the top here. So, there's lots of math here, but then when you drill down, you start seeing really having to have awareness of your memory hierarchy in order to squeeze the performance out. So there's future work here, making it software, or almost ready for 1.0 release as part of the Chombo distribution. We're still exploring the design trade-off space. Patch size, N or alpha, overlap, alpha, harmonic order of accuracy. These all trade in different ways that can affect performance, can affect accuracy. In some ways, they're not trade-offs. They're, Q equal 10 sounds like a really good idea no matter what, because there's no penalty for it. It turns out it's more difficult to program, and that's why we haven't fully implemented it yet. We really need to take a deep dive into FFT. There's a substantial amount of difficult platform-dependent work to get high-performance Hockney kernels. This kind of work can be automated. In fact, FFTW was an example of how you automate it. FFTW was written by a couple of smart graduate students at MIT in the mid-90s. And what did they do? They created an engine for essentially a domain-specific language for expressing FFTs. They had a symbolic analysis engine for transforming that, and a tuning engine for figuring out variance, and a code generation. We've been using their generated code for a couple of decades now. And the kind of, as has been pointed out here, the thread's kind of running out here. We need to revisit that. And in fact, it's a project I'm working on to revisit exactly that. And then on the more mathy side, fast local convolutions suggest an alternative approach to solving constant coefficient PDEs. So for example, use convolution methods for Maxwell, method of spherical means instead of doing a finite difference time evolution method. Fast evaluations for high order stencils. As we move to high order moves you to the right on your roofline. So if you can kind of get the accuracy from doing more floating point, that's great. But at what point does it make sense to use an FFT rather than an explicit stencil from a performance standpoint? Well, it depends on how good your FFTs are. Final comments. There's a wonderful line here that from my undergraduate advisor from a paper he wrote. We make very limited claims to the novelty for the methods presented here. The ideas involved are quite standard and indeed old-fashioned. And so by way of evidence, Hockney's algorithm goes back to 1970. The main ideas in MLC, which are finite difference localization, in this case for boundary integrals, was done as a PhD thesis by Anita Mayo at NYU in 1984. And Chris Anderson developed the first MLC algorithm, but it was really for doing fast evaluation of particles. So it's like a P-cubed-M method. The other takeaway from this talk is that changing the math can have a large lever arm. We didn't go and futz around with trying to make multigrid faster. We said, we need to think about this problem differently. And then finally, I need to mention my collaborators, Scott Baden, Greg Balls, Christos Kavouklis, Peter McCorkadale, and Brian von Strahlen. And this has been an ongoing effort for a long time, but I think we're finally seeing the finish line. All right, I'll stop here. Thank you.